In 10 years, it'll be 1, 1, 2, 2, 3, 3. It's kind of fun. All right. So here's question 6a. What is the equation of the plane that contains the point -3, 4, -2, and has normal vector n equal to 5i plus 2j minus 3k. And if you don't like that notation, you could totally just, when you see that, you could go ahead and rewrite it as n equal to 5 to -3, if that is preferable. Either way is totally fine. Okay, here's how I would imagine he would most like you to answer a question like this on your exam. You should probably draw a little picture of your plane. Draw your normal vector sticking up out of it perpendicular. Draw the point right there, the point -3, 4, 2. Sorry, -3, 4, -2. And then draw a vector from that point to another point in the plane, which we call x, y, z. And make sure you indicate that the angle between those two vectors you've just drawn is 90 degrees, because it is. I also personally would label this vector. I would call it V or A or whatever letter you like to choose. Anything is fine, except for N. You shouldn't use something you've already used. And then, because I know what N is already, I'm going to write down what V is. V is the vector that starts at that point and ends at that point. So it's these coordinates minus those coordinates. So the first coordinate is, or component, I should say, really, is x minus -3. And then the second is y minus 4. And the third is z minus -2. If you're like me, you should be extra careful when you're writing your z's and your 2's next to each other, because they start to look kind of the same. So just be extra careful when you're writing things. So I would write this as either x plus 3, comma y minus 4, comma z plus 2. Or if you're an IJK kind of person, you could also write this as x plus 3i plus y minus 4j plus z plus 2k. Either way is totally acceptable. It just is really what you prefer. Okay, here's the whole crux of this thing. These two vectors are perpendicular or orthogonal or normal. Pick your favorite word. And you all should be able to tell me that vectors that are orthogonal to each other, their dot product is equal to what? Right. So that's the thing we're going to use here, is the fact that we know that n dotted with v must equal 0. But then we're actually going to write it out. So n dotted with v, well, n is the vector, and I like this notation better. 5, 2, -3, dotted with the vector that we just wrote here, x plus 3, y minus 4, z plus 2, and that should equal 0. And now we're going to multiply it out. Or I should say we're going to dot it out. We're going to take the dot product. So we're going to get 5 times x plus 3 plus 2 times y minus 4 plus -3, I should have written minus, oh well, times z plus 2 equal to 0. And technically, if it doesn't say that you need to like write it in the standard way, this is a perfectly acceptable answer. And if you're short on time, you could leave your answer like this. If you wanted to simplify it, you certainly can. The more typical way of writing the answer would be to multiply this out and get 5x plus 15 plus 2y minus 2 minus 3z minus 6 equal to 0. And then I made a mistake though. Not 2y minus 2, 2y minus 8. Right, distribute the 2. And then 15 minus 8 is 7. 7 minus 6 is 1. Subtract 1 from both sides to get 5x plus 2y minus 3z equal to -1. That's the more typical way of writing your plane equation. But both are technically the same equation, and both are right. Okay, let's say you get to this question. Oh, question.
It's an equation that's like ax minus 0, b y
This is exactly that. Yes, so you could totally jump to saying you could basically start with your A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0. That is totally fine. I would also point out, if you really want to do it fast, you could also start with AX plus BY minus plus CZ equal to D, and then plug in your point to solve for D. Plug in X, Y, Z equal to negative 3, 4, 2. Sorry, negative 3, 4, negative 2. And then you're going to get 5 times negative 3 plus 2 times 4 minus 3 times negative 2. And negative 15 plus 14 is negative 1. So my equation is 5x plus 2y minus 3z equal to negative 1. And certainly I think that's fine. I could just see him asking the question in a way where he might want you to show some of this work here where you're dotting the two vectors together and getting the equation. Or not. I don't actually know because I haven't seen him write the test for this. So we'll see. Questions about that? Okay. The thing you should always be looking for is that the coefficients of x, y, and z should literally be the components of your normal vector, a, b, and c. Cool. Let's look at 6b. 6b, find a non-zero vector. When we say a zero vector is the vector where every component is 0, a non-zero vector that is perpendicular to the vector v equal to 3, negative 7, 2. There are literally an infinite number of possible correct answers here. So again, we're exploiting the fact that perpendicular vectors have to have a dot product that is equal to 0. So you could really easily make something up. Like I could pick, without doing any sort of work, I could say u equal to 7, 3, 0. That's going to totally work because v dotted with u is equal to 3 times 7 plus negative 7 times 3 plus 2 times 0. And that's going to be 21 minus 21 plus 0, which is 0. That checks out. But maybe it's not going to be so easy to see, or maybe someone's going to make it harder way. The more kind of methodical way of doing this is say, okay, let's say we want to just say, I want u. I don't know what u is yet. I'm going to try and make it up. So u is going to be u1, u2, u3. And I know that v dotted with u needs to equal 0. So v dotted with this u is going to be 3 times u1 plus negative 7 times u2 plus 2 times u3. Let's say he made it hard by saying all of the components of u have to be not 0. Not just that it's a non-zero vector, but I don't want a 0 there, there, or there, just to make it extra hard. Okay, so now I can't have any of these equal to 0. So here's what we're going to do. We're going to pick 2 of the numbers. And I'm going to pick it so it's not nice, just to make it so you can see what's really going to happen here. So I'm going to pick, sure. Yeah. Let's say I pick u1 equal to 1 and u3 equal to 1. And then I'm just going to solve for u2. So looking here, I have 3 minus 7u2 plus 2 equals 0. So, get out of the way. So I can solve here. I can say 3 plus 2 is 5. I can add 7u2 to the other side. So u2 is going to equal 5 divided by 7. So here's a much less nice vector to write, but it's still correct. We could make the vector be 1, 5/7, 1. And that would also be perpendicular to our vector v. Because the dot product of that and that is still going to be 0. 3 plus -5 plus 2 is equal to 0. So if they ask you to find a vector perpendicular to another vector, it's usually like you can just make one up usually pretty quickly without having to do a lot of work. What I really did here, which is a common trick, is you take the first two terms, you interchange the places they are, and you change the sign on one of them. So I interchanged the 3 and -7, I made it -7 and 3, and then I changed the -7 to a +7. And then make 0 the last part, because that won't change anything. That'll always work if you're trying to find a vector perpendicular to another vector. It's kind of cool. Questions? Correct. That is not a valid answer. That's totally valid. So I want to point out, yes, I was hoping someone would ask that. This here, even though there is a 0 in it, this is not the 0 vector. The 0 vector, written like that, is the vector where all 3 or however many components, although usually 2 or 3, because that's how many, those are the dimensions we were dealing with here. That's your 0 vector, just the vector with 0, 0, 0, like that. Or if it's in 2 dimensions, 0, 0. Yeah. Other questions? All right, let's continue to work backwards unless there's something specifically. Yeah. Sure. Just jump around. Jump up, keep up, and get down. Sorry, I'm sure that's way before all your thing. Okay, 4A. So we've got the prompt is solve the following. We might want to see the differential equation. We want to solve the following differential equation: x squared y to the 4th dy dx minus 3 equal to y to the 5th. I'll be perfectly frank. I didn't make this problem up. I just grabbed it from somewhere. And the first 2 times I tried to do it, I made mistakes because I really thought it was going to be first order linear, which was not right. Let me show you what I tried to do, just so you can be aware of how you can see that that's not the right thing to do. I would usually look for separable first, but someone wrote it in a way that kind of think, well, it could probably be first order linear. Let's try. So I was trying to write it like this. I was like, well, if I divide, actually I did this first. I did x squared y to the 4th times dy dx, or if you prefer y prime. And I subtracted the y to the 5th, and I added the 3. And the reason I did that was because I thought I was going to be dividing by y to the 4th, and so I was going to get a y there, which actually wasn't wrong. Here's where I encountered the problem. So I divided everything by x squared y to the 4th, which I thought was going to work out just fine. Here I got dy dx. Here I got y to the 5th over y to the 4th, and then I also had a 1 over x squared just to kind of separate them from each other. And that's just a y. Oh, I'm looking good. I'm like, I've got y prime. I've got my -1 over x squared is acting like my p of x times y. But then on the other side of this equation is where I ran into a problem. I had 3 over x squared times y to the 4th. And specifically, that y to the 4th is a no, right? If I want to do it first order linear, this right side, after I write it in the standard form, has to be a function of just x, or whatever your independent variable is. So this is not a integrating factor first order linear problem, even though I thought it was when I started off. So if you've eliminated one option and they told you to solve it, you have to be able to do it the other way, unless someone wrote a bad problem. Right? These are the only 2 ways we know. We can either do it first order linear with an integrating factor, or we can do it as a separable equation. So since it's not first order linear, it has to be separable, or it's unsolvable for us. But they said solve it, so. All right, so if I'm trying to separate things, I'm really just going to get dy dx all by itself. So I'm going to take this equation, and first I'm going to add the 3 to the other side. So x squared times y to the 4th times dy dx equals y to the 5th plus 3. And then I probably think it's easiest to actually divide by whatever's over here, just so I can get dy dx by itself and start thinking about what I want on what side. It's probably doing extra work to divide by y to the 4th, and I'm going to want to leave it on the other side, but fine. So I've got y to the 5th plus 3 over x squared y to the 4th. And now that I have this by itself, I really have to be able to express the other side as a function of x multiplied by a function of y. And I can. It's 1 over x squared times everything else. Y to the 5th plus 3 over y to the 4th. And now I separate. So I'm going to get all the y's on the left, all the x's on the right. Instead of dividing by y to the 5th plus 3 or y to the 4th, we should just multiply by its reciprocal. So we're going to say, great, we're going to have y to the 4th over y to the 5th plus 3 times dy equal to, on this other side, I'm going to be left with just 1 over x squared times dx. Right, from this equation here, from this equal to this, I multiply both sides by y to the 4th over y to the 5th plus 3. And now we're ready to integrate both sides. So the integral of y to the 4th over y to the 5th plus 3 dx should equal the integral of, dy, holy smokes. I should rewrite this as x to the -2. One of these is pretty easy. I mean, they're both not terrible, but the right-hand side is a straight shot. We know how to integrate that. This right-hand side is going to be x to the -1 over -1 plus c, which I would encourage you to write as -1 over x plus c. But then we have to do the left-hand side. And for the left-hand side, we have to do a u sub. So we're going to let u equal the denominator because its derivative is almost exactly the numerator. The derivative of y to the 5th is 5y to the 4th dy. So dividing both sides by 5, 1/5 du is equal to y to the 4th dy. So we can rewrite this as the integral of y to the 4th dy becomes my 1/5 du over y to the 5th plus 3 is just what my u is. I would rewrite this as 1/5 integral of 1 over u du, which is 1/5 natural log of the absolute value of u plus, I don't need the plus c here, which is 1/5 natural log of the absolute value of y to the 5th plus 3. But then we're not done, because they said to solve it, which means you're supposed to isolate y if possible. So what we're going to do now is we're going to set these two things equal to each other and solve for y. And I will tell you, even though I didn't do it in the solutions because I just couldn't help myself, you really should make your life easier and drop the absolute values. I know it's not easy for me to do because it always feels like I'm cheating, but it's really not. I should really just write 1/5 natural log of y to the 5th plus 3 equals -1 over x plus c. And don't worry about it, even though that's advice I can't follow myself. Solve for y. Multiply both sides by 5. So the natural log of y to the 5th plus 3 equal to -5 over x. And 5 times a constant is still a constant. And then exponentiate both sides. So e to the natural log of y to the 5th plus 3 is equal to e to the -5 over x plus c. The left-hand side becomes just y to the 5th plus 3. The right-hand side is e to the -5 over x times e to the c. You know, I'm going to call that a. So then subtracting 3 from both sides, we have y to the 5th equals a times e to the -5 over x minus 3. Sorry, I started to write plus and fixed it at the very last second. And then finally, take the 5th root of both sides to get y equal to the 5th root of a e to the -5 over x minus 3. And without any initial conditions, that's as good as it gets. It's kind of a lot. The algebra here, I feel like this problem is maybe a little more extra than you would actually see, but more because not so much the integrating part, but the actual solving for y is a little bit irksome here, but not the worst ever. Yeah. I'm just calling, that's the letter I like to choose. You could call it C if you like, that's totally fine as well. Or literally any letter you want that is not one you're already using. I just use A because I don't know, I just do. That's some textbooks do it that way for some reason. They're really because we're saying A is plus or minus e to the c, and so, but it's fine to call it C. It's totally fine. Yeah.
So when we're solving differential equations, do we try to like solve it when it's the first order linear first, or is it something?
We always, so whatever kind of differential equation it is, at the end of the day, we are always trying to find y equal to whatever. That is the solution, y equal to whatever the function is. So we finished integrating right here. But we hadn't solved it yet because we didn't figure out what y was. And since we're already on the topic of solving differential equations, let's look at 4b. So 4b. So when I wrote this test, I thought both of these were first order linear, but they're clearly not. But the second one is first order linear. So starting off, we have x squared times dy dx plus 3xy equal to sine of x. And so I need to get it in the proper format. I'm going to divide everything by x squared. So we're going to get dy dx. 3x divided by x squared is 3 over x times y equal to sine of x over x squared. Looks worrisome. I don't know how to integrate that, but don't worry, we don't have to integrate that because we're going to multiply by whatever integrating factor is. But it looks like, I feel like when I started doing this problem, I was worried. I was like, oh, did I assign a problem that's not doable? I didn't, but it's good lesson. Like, just because things look bad in the beginning doesn't mean they're actually going to be that bad. So now let's find our integrating factor. Mu of x. Oh, and if I were writing this, I would label things. I would either circle this and say it's equal to p of x or whatever you want to do. Also, I would circle this and say it's equal to q of x. Be careful. Pay attention to the sign there. If that's a plus, your p of x is positive 3 over x. If that's a minus, your p of x is negative 3 over x. The sign goes with the p of x, not with the y. So our mu here is going to be e to the integral of p of x. That's going to be e to the 3 times the natural log of x, which you definitely should always simplify. That's going to be e to the natural log of x cubed, which is just x cubed. And then I think he wants you to show this work. If he doesn't, you can jump straight to the answer. But I would do the work of multiplying everything in this equation by x cubed. So multiply your standard equation, or standard format, by mu of x equal to x cubed. So we're going to get x cubed times dy dx plus x cubed times 3 over x times y equal to x cubed times sine of x over x squared. And I think you can skip this step straight to the simplification, which is that we're going to have x cubed times, I'm going to write y prime instead of dy dx. X squared times 3 over x is 3x squared times y. And x cubed times sine of x over x squared is just x times sine of x. One thing I like about this example is I think it's pretty obvious. The left-hand side really is a product rule derivative. I think we can see that, oh yeah, this here is just the derivative of x cubed times y. Take the derivative of x cubed times y, you get 3x squared times y plus x cubed times the derivative of y. So that all there is the same as that. The right-hand side hasn't changed. But then we integrate both sides, and we get x cubed times y equal to the antiderivative of x times sine of x. This is also a good problem because it makes you do integration by parts as well. But not like a terrible integration by parts, right? It's a one-step integration by parts. So for integration by parts, our u is going to be x. Our dv is the rest. Whenever you're doing integration by parts, just remember, you pick your u via LATE, late, and then dv is everything else. In this case, sine of x dx. Our du is 1 times dx. Our v is the antiderivative of sine, which is negative cosine of x. So solving this, This is gonna have, we're gonna have x cubed times y equal to u times v. So instead of writing x times negative cosine, let's put the negative out in front and write it as negative x times cosine minus the integral of negative cosine dx. Okay, and so then we're going to get x cubed times y equal to negative x times cosine of x. And this is really plus the integral of cosine, right? A minus is plus. And the integral or antiderivative of cosine is positive sine. And then we have to have the plus c. Finally, we can solve for y by dividing by our integrating factor here. We get y equal to all of this divided by x cubed. I think in the solutions I like divided each part by x cubed, but this either way is fine. No, you don't. Here's why. So the idea basically is if you have this, like if you had x cubed y plus c1 and you had it equal to negative x cosine of x. Yeah, sorry, did you mean that integral there or did you mean the one up here? No, so for the one up here, we just totally ignore it. We don't need a plus c. Yes, and the reason why is because if you had a plus c, then you would you'd be multiplying by an e to the c, right? And if you're multiplying by an e to the c, what that would do is when you multiply everything by this, you would just be multiplying the entire equation by a constant as well. That's not going to really make a difference, right? You can totally divide both sides by that constant to get rid of it. So we don't need to introduce it in the first place. And just to answer the question that wasn't asked, if you did have a plus c on this side when you integrated and on the other side when you integrated, we would just then say, oh, well, let's subtract that over there and say we have really c2 minus c1, and let's call it a new c. So that's why you don't need a c on both sides there. Because it was a minus a negative cosine. And so I just changed, instead of writing it again, I just changed the signs. Yeah. I don't know. Maybe. I feel like that's not usually what happens, but here's what I say. I would imagine for sure there will be at least one differential equation that you will have to solve and then plug back in your initial condition to find C. To that end, let's look at problem previous 3B. Well, we should do both parts. Should we do both parts? Is there going to be an Euler's method question on this test? Yeah. Wow, maybe. Okay. So let's do 3B first, and we can decide as a group if we want to do 3A or not. So 3B. 3B says solve the differential equation, which is dy dt equal to t times y, and use the initial condition y of 0 is equal to 2 to solve for any constants. So first, just the solving. So this is at the end, right? After you solve, then use this to solve for C. Or I should say find, then use this to find any constants. Okay, so this one's definitely a separation of, I mean, I guess you could do this one as a first order linear if you really wanted to, but separable, right? We should do the separable one. So I'm going to have 1 over y dy equal to t times dt. And then we're going to integrate. Integral of 1 over y dy equals the integral of t times dt. We end up getting the natural log of the absolute value of y, but we don't really need to write that, James. Yeah, I still want to write it though. Is t squared over 2 plus c. And then we're going to solve for y. So I'm just going to drop the absolute value. Y is going to be e to the t squared over 2 plus c, which is e to the t squared over 2 times e to the c. Wow, that's a t? Okay. And that's going to equal e to the t squared over 2 times, let's call it c. And that's our solution. So our general solution is y equal to c e to the t squared over 2. But then we have to find what c is. Our initial condition is that when t is 0, y is 2. So plug in your initial condition or initial value, and you're going to get y is equal to 2, and t is equal to 0. 0 squared is 0, 0 divided by 2 is 0, e to the 0 is 1. So we end up getting 2 is equal to c times 1. So c is equal to 2. Now, the thing about this is that when you do find this constant, you then really should go back and plug it into your solution. So our actual particular solution is just the general solution with your constant value actually solved for and plugged in. It's going to be y equals 2e to the t squared over 2. All right. So usually finding the c values, I mean, this one I feel like is pretty easy to find the c value for. There's not a lot of solving, but the idea is still the same. Once you have found your general solution, you're plugging in the value of y and the value of t and solving for the constants that are in there. Make sure you put them in the right place, right? The thing that is like y of the thing, the of part, that's what t is, and the y of equal to, the equal to part is what y is actually equal to. Can be confusing. I know sometimes people want to plug in a 0 for y here, but that's the wrong choice. Y is equal to 2 when t is equal to 0. In fact, if you see this, I recommend writing, oh yeah, t equals 0 and y equals 2. So then you know when you plug it in later what to plug in for what. Okay. We'll come back to Euler's method if we need to, if we have time to. Yeah. Yeah, let's go over all of 2 actually. I mean, I guess, yes, but let's go. We can do 2D first because 2D is different than the rest of it. Because I would say A, B, and C are all related, but 2D is not. So 2D. Without graphing the phase plane, find and classify the equilibria of the differential equation. Our differential equation dy dt equal to y squared minus 4y plus 3 over y plus 1. We want to find and classify the equilibria using the non-graphical method, right? We're trying to do the other thing, not the graphing thing, without graphing. Okay, so first the find part. To find the equilibria, we set the derivative equal to 0. So set y squared minus 4y plus 3 over y plus 1, right? I said the derivative, I didn't take the derivative because the derivative dy dt is equal to y squared minus 4y plus 3 over y plus 1. Okay. When you're setting a fraction equal to 0, we really just care about when the top is 0 because we don't want to divide by 0. That's not equal to 0. That's undefined. So we're really just going to look at y squared minus 4y plus 3 equal to 0. And that factors as y minus 3 times y minus 1. So our equilibria are y equal to 3 and y equal to 1. But which one is stable? Which one is unstable? Are they both stable? Are they both unstable? Is one of each? We don't know yet. We have to find out. So the way we're going to find out is by taking the derivative of this expression. So this is usually where someone does something like, we're going to call this g of y or f of y. Or I think g is the usual choice. So g of y is equal to y squared minus 4y plus 3 over y plus 1. And we're going to find the derivative of that. Because if the derivative is negative, it means you're going from positive to negative, which means you're having a stable equilibrium. If the derivative is positive, it means you're going from negative to positive, meaning the negative parts go that way, the positive parts go that way, and you have an unstable equilibrium. But we have to find the derivative before we can do any of that. So, okay, great times. Quotient rule. I tried to make a function that was hard here, so that we just so that it was challenging. So we're gonna do the bottom times the derivative of the top, which is 2y minus 4, minus the top, which is y squared minus 4y plus 3, times the derivative of the bottom, which is 1, all divided by the bottom squared. Do we need to simplify this and multiply it out? Not really, actually. I did in my notes because I wanted to, but really, I think I can plug in 1 and or 3 and be careful and get the values without actually simplifying this. Would it be easier to simplify it first? Maybe, maybe not. Let's plug in and see what happens, and then maybe we'll talk about simplifying it. So I plug in 1. G prime of 1 is going to be, let's see here, I'm going to get 1 plus 1 times 2 minus 4 is -2 minus, in parentheses, 1 minus 4 plus 3. Oh, that's actually, you're smart, James. The bottom's going to be 1 plus 1 squared, which is positive. So looking at what I've got here, 2 times -2 is -4. 1 minus 4 plus 3 is what? 0. Which is not surprising because we're plugging in the value of 1 that made this original top part equal to 0. So it's not surprising when we plug it in there to the original top part that hasn't been changed, you get 0. All over 2 squared, so we get -4 over 4. And I don't care that it's equal to -1, I just care that it's negative. Which means we have a stable or an unstable equilibrium here. Stable, great. So y equals 1 is stable. Let's see what happens when we plug in 3. Okay, so looking at this again, I'm going to get 3 plus 1 times 2 times 3 is 6, minus 4 is 2, minus, again, when we plug in 3 over here, we're going to get 0. 9 minus 12 plus 3 is 0. All divided by something that's for sure going to be positive. So we have a positive number over a positive number, that's positive, which means y equals 3 is unstable. So that was the gist of this problem. And I do think it's, in retrospect, I think it's probably easier to not try and simplify this numerator if we know we're just gonna have to plug in a couple values for y. Yes. By -1. Sorry, say I thought you guys was different. Go ahead. Well, so what happens if you plug in -1? If I plug in -1, g of -1 is equal to, can you see that all right? Yeah, maybe. G of -1 is equal to 1 plus 4 plus 3 over 0, which is undefined. To be in equilibrium, we have to be in a place where things are not changing. And for things to not be changing, the derivative has to be 0, not undefined. Undefined is problematic as far as we're concerned. So yeah, that's why -1 is not being looked at here. So y equals -1 is not an equilibrium. More importantly, in this problem, it's not even in the domain of this expression, right? So it's not even something that's up for grabs. All right, what time is it? About 12 till. What else should we look at? Yeah, I can't. I did not explain that in the solution. Sure. So for 1b, and I'm just going to draw the pictures. Here we go. So we're going to set up an interval for the, well, let's label things here. We want the volume of the solid obtained by revolving the region bounded by f of x equal to 6 minus x, g of x equal to the square root of x, and x equal to 0 about the x-axis. And I do think it's really worth your time to draw these regions. Not the volume, like don't rotate it around the axis, don't try and draw the 3D shape, but definitely draw the 2-dimensional region that is getting revolved. All right, so I know basically what these look like. G of x equal to the square root of x looks like this. And f of x equal to 6 minus x is a straight line, has a y-intercept of 6 and an x-intercept of 6, so it looks something like that. And importantly, x equals 0 is the vertical axis. There's x equals 0 right there. And there's f of x equals 6 minus x. So we are looking at this region here between x equals 0, g of f of x equals 6 minus x, and g of x equals the square of x. Not that little region right there. Be careful. It's easy to accidentally get this one listed that way. So how did I find this point here? Well, the real truth is I guessed. I didn't set these equal to each other and square both sides and try and solve it. Although you totally could, or you could totally say square root of x equals 6 minus x, square both sides. You get x equal to 36 minus 12x plus x squared. Subtract x. You write this in the more normal way. Minus 12 minus 1 is minus 13. And then the right side factors as x minus 9 times x minus 4. And you end up getting x equal to 4 or x equal to 9. But x equal to 9 is the one that's down here. But what I really did, I didn't do any of that. What I really did was said, okay, well, the person writing this problem is probably not a jerk. And they probably picked a value that's easy to figure out. And oh, there's not a lot of numbers between 0 and 6 that I know how to take the square root of and get a nice integer result. So I plugged in 1. Oh, it didn't work. Square root of 1 is 1, 6 minus 1 is 5. I plugged in the next square number I've got, which is 4. Square root of 4 is 6 minus 4 is, oh, they're the same. That's the point where they intersect. And honestly, that is the way a lot of people are actually doing these. They're looking for the lowest hanging fruit. They're like, oh, it's probably going to be something easy. Just plug in the easy values until you've gotten it or until you've exhausted them. And then you actually have to go try and solve it. And then the rest of this is, well, let me ask you all. For my region here that's revolved around the x-axis, am I using the disk method or the washer method? Washer, because my region is not flush against the axis of rotation. So I'm revolving this strip that is perpendicular to my axis of rotation around the axis, and I'm getting a shape that looks like it's not my best ever, but I'm getting a shape that looks kind of like that. Oh my gosh, yeah, good job. Okay, sorry, there's my wonky looking washer there, but the volume of that washer, as is the volume of every washer, is pi times the larger radius squared minus pi times the smaller radius squared, all times the thickness, which is dx. The larger radius is the function that is further from the axis of rotation. In this case, it is f of x equals 6 minus x. That is my larger radius. My smaller radius is the function that is closer to the axis of rotation. In this case, it's g of x equal to the square root of x. So when I write this here, it's going to be factor out the pi. It's going to be big R squared, which is 6 minus x, quantity squared, minus little r squared, which is the square root of x, quantity squared. And then we're going to integrate that from x equals 0 to x equals 4. And if it were me, I would leave that as the square root of x squared, because they're only asking us to set it up, and leaving it like that really indicates that you know what you are doing. Oh yeah, it's this thing squared minus that thing squared. So I wouldn't simplify that. Okay. What else should we look at in the last 7 minutes here? Cool. So look at 2C. I think we have to look at A and B. Let's see. Yeah. Okay, yeah. 2C is, yeah, we should look at A and B because it really is required here. And it's not that bad to look at A and B. So 2A, draw a phase plot for the differential equation dy dt equal to y minus 2 times 4 minus y times 7 minus y. The equilibria are 2, 4, and 7. So if we're doing y on the horizontal axis, dy dt on the vertical axis, 2, 4, and 7 are our intercepts. And then you just have to figure out for one of them which side of the horizontal axis you're on. So I would literally pick the value, if I plug in y equal to 1, which is between, it's left of 2, dy dt. I don't actually care what it's equal to, I just care if it's positive or negative. It's going to be 1 minus 2 times 4 minus 1 times 7 minus 1, and that is a negative number. I really, really don't care that it's equal to negative 18. I just care that it's negative. So I'm down here. And then since each of my equilibria come from factors with odd powers, we're going to cross the axis every time we get to them. So we're going to look something like this. Cross, cross, cross. Your picture does not have to be even close to perfect. Oh, sorry, you can't see all what I'm writing there. Apologies. So we did part 1. Part 2, we still need to draw on this thing though. So 2B is to determine the stability, and that's by drawing the little arrows. So if your graph is below the horizontal axis, your arrows point which way? To the left, where to the y is decreasing direction. And if your graph is above the horizontal axis, your arrows point to the right. And if you're below, they point to the left. And if they're above, they point to the right. So that means that y equal to 4 is, and the other two are unstable. So now, 2C. Let me ask you all. If our y value started, let's see, we're told that y of 0 is equal to 6. So if y started right there, so at t equal to 0, which is not on this graph anywhere, right? There's no t on this graph. But if t did start at 0 and you got y equal to 6, what direction is y getting pushed in? Getting pushed towards 4. So as time progresses, y is going to get pushed closer and closer and closer to the stable equilibrium 4. Now, here's how some people do this. You can make the graph of y versus time, and we can see that y equal to 4 is a stable equilibrium. So let's see. 1, 2, 3, 4, 5, 6, 7. So here are our equilibria, stable or unstable. Sorry, can I draw them? Maybe. So here's y equals 7, y equals 4, y equals 2. And the thing is, if you start anywhere between 2 and 2 and 7, you're going to get pushed towards 4. So like if my initial condition is y of 0 equals 3, well, I'm going to get pushed towards 4 as time goes on. Or if y of 0 equals 6, I'm going to get pushed towards 4. But if I start on the wrong side of my unstable equilibrium, like if I started up here, I would get pushed way away because I'm going larger and larger and larger and larger. Or if I started down here, I would get pushed way away like that. But since I'm starting between a stable and an unstable one, I'm going to get pushed towards the stable one, which was 4. And in general, that's what's happening here, right? If you have some limit as t goes to infinity and they're told where you start, you just have to look at, okay, I'm starting here. Which direction do I get pushed in? Well, I get pushed over towards that stable equilibrium here. On the other hand, if someone asked the question, if y of 0 equals 8, what is the limit as t goes to infinity of y of t? Well, now if we're starting here, we're just getting pushed further and further to the right, which means y is getting larger and larger and larger. So in this case, the limit as t goes to infinity of y of t would also be infinity, because we're just getting the y's are just getting, you start here, the y's are just getting bigger and bigger and bigger and bigger and bigger. There's no end.
What would you like to answer for your time?
That's a good question. I would say I would probably write the answer here as I would probably literally just write the limit as t goes to infinity of y of t equals 4, and then say because of the graph. You could also draw this thing here, but it's kind of annoying to draw this. And I don't think you talked much about this in your class. So I like, I don't know if he's actually gonna ask a question like this. I know I've seen other people ask questions like this, but they've talked more about this idea. So it probably won't show up, but I wanted you to see it just in case it did, so, yeah. All right, it's 2:59. Let's call it a day. Good luck on your exam. I'm sure you're all gonna do just fine. Have a lovely Thanksgiving. I'll see you all on Monday. If you're here, I'll be here. If you're not here, that's also okay.